hydrogen is not just a lighter version of natural gas. And that single misunderstanding is responsible for more bad hydrogen engineering decisions than almost anything else in this industry. If you treat hydrogen like methane, your pipe sizing will be wrong, your ventilation will be wrong, your material selection may be wrong, your relief modeling may be wrong, and under system stress, your project may fail before it ever reaches bankability. Today we're going to break this down at the physical level: density, viscosity, thermal conductivity, diffusivity, Joule-Thomson behavior, flammability, embrittlement. And by the end of this video, you will see why hydrogen systems require a fundamentally different engineering mindset. Now look at image 1. This is the physical property comparison between hydrogen, methane, and air. Hydrogen's molecular weight is 2.016 grams per mole. Methane is 1604. Air is about 28.97. That difference may look like a chemistry trivia fact, but it drives everything downstream. At standard conditions, hydrogen has a density of 0.0899 kilograms per cubic meter. Air is 1.225. Methane is 0.6 teravan. Hydrogen is 14 times lighter than air and roughly 8 times lighter than methane. That means if you want to move the same mass of hydrogen as methane, you must move dramatically more volume. And engineering equipment does not respond to mass. Pipes, valves, compressors, and flow meters respond to volumetric flow and velocity. Now move to image 2. This illustrates the volumetric consequence of that low density. Consider a 10 megawatt electrolyzer producing 500 kilograms of hydrogen per hour. At standard density, that corresponds to more than 5,500 cubic meters per hour. If you were moving 500 kilograms per hour of methane, the volumetric flow would be a fraction of that. Hydrogen systems are volume-intensive systems. That means pipe diameter becomes a first-order design variable. Undersize the pipe and velocity climbs. When velocity climbs, friction losses increase. When friction losses increase, compressor power increases. When compressor power increases, operating cost rises. This is how a molecular weight of 2.016 grams per mole eventually affects your levelized cost of hydrogen. Now look at image 3. This is where fluid mechanics changes regime. Hydrogen's viscosity at standard conditions is approximately 8.76 times 10 to the minus 6 Pascal seconds, roughly half that of air. Combine low density with low viscosity and you get something very important. Hydrogen reaches fully turbulent flow at lower mass flow rates than most industrial gases. Reynolds number is defined as density times velocity times diameter divided by viscosity. Lower viscosity increases Reynolds number. For the same mass flow in the same pipe, hydrogen's Reynolds number is roughly double that of air. That means hydrogen systems tend to operate in the fully turbulent regime almost immediately. Turbulence affects friction factors, pressure drop correlations, heat transfer coefficients, vibration behavior, and noise generation. You cannot simply reuse methane pressure drop tables and assume accuracy. Now turn to image 4. This is the thermal conductivity comparison. Hydrogen's thermal conductivity is approximately 0.1805 watts per meter Kelvin. Air is around 0.025. Hydrogen conducts heat roughly 7 times better than air. In an electrolyzer stack, this is beneficial. High thermal conductivity improves heat removal. It reduces hotspot formation. It helps maintain membrane stability. But move to storage or pipeline transport, and the same property creates insulation challenges. Heat ingress into cryogenic tanks becomes more aggressive. Temperature equalization along pipelines occurs more rapidly. Hydrogen transfers heat more efficiently than most gases. That means thermal modeling must be precise. Cooling systems must be designed with hydrogen's conductivity in mind, not methane's. Now consider mass transfer behavior. Look at image 5. Hydrogen's diffusivity in air is approximately 6.1 times 10 to the minus 5 square meters per second. Methane's diffusivity is about 4 times lower. Hydrogen disperses rapidly. Outdoors, this is an advantage. A leak tends to rise and dilute quickly because hydrogen is buoyant and diffusive. It does not pool at ground level like heavier gases. But indoors, that same property means hydrogen can accumulate near the ceiling very quickly. Ventilation design must account for buoyancy. Air intake should be low, exhaust high. Ceiling level gas detection becomes critical. Hydrogen's molecular size also introduces permeation issues. It can migrate through polymers and elastomers that easily contain methane. Seal selection becomes an engineering decision, not an afterthought. Now move to image 6. This is one of the most counterintuitive hydrogen properties, the Joule-Thomson effect. Most gases cool when they expand at room temperature, and hydrogen does not. At ambient temperatures, hydrogen has a negative Joule-Thomson coefficient. That means when it expands through a valve, it can heat rather than cool. The inversion temperature for hydrogen is around minus 80 degrees Celsius. Above that temperature, expansion leads to heating. This matters for pressure relief valve design. It matters for rapid depressurization modeling. If you assume hydrogen cools like methane during blowdown, you are modeling the wrong thermodynamics. Under certain conditions, rapid pressure drops can increase temperature, not decrease it. Now consider combustion characteristics. Hydrogen's flammability range in air is 4 to 75% by volume. Methane's is roughly 5 to 15%. Hydrogen's ignition energy is 0.017 millijoules, nearly 1/10 that of methane. Its flame speed is about 3.46 meters per second, roughly 8 times methane's. That means hydrogen ignites more easily and burns faster. Yet hydrogen flames are nearly invisible in daylight and emit low radiant heat. Visual detection is unreliable. This is why hydrogen facilities rely on catalytic sensors, infrared detection, and acoustic monitoring. Codes such as NFPA2 and IEC 600-79-10 provide guidance on hazardous area classification and ventilation requirements. Hydrogen safety design is not optional redundancy. It is a direct response to physical properties. Now turn to image 7. This is hydrogen embrittlement. Hydrogen atoms are extremely small. They can diffuse into steel crystal lattices, especially under high pressure and stress. Over time, this can reduce ductility and promote crack growth. Higher strength steels are often more susceptible than lower strength grades. This is why hydrogen piping design references ASME B31.12. The code provides derating factors for allowable stress in hydrogen service. A steel grade that performs safely in natural gas service may require reduced allowable stress in hydrogen service. That can mean thicker pipe walls and higher capital expenditure. Hydrogen challenges the assumption that stronger steel automatically means safer design. Fracture mechanics and hydrogen compatibility matter more. Now let's integrate these concepts into a worked example. Look at image 8. Suppose hydrogen flows at 30 bar and 25 degrees Celsius with a mass flow rate of 500 kilograms per hour. Using a compressibility factor near 1.012, we calculate density at these conditions of approximately 2.42 kilograms per cubic meter. The volumetric flow becomes about 206 cubic meters per hour. In a 100 millimeter diameter pipe, velocity is approximately 7.3 meters per second. Using hydrogen's viscosity, Reynolds number exceeds 200,000. That is fully turbulent flow. Pressure drop must be calculated using the Darcy-Weisbach equation with an appropriate turbulent friction factor. If you reduce pipe diameter, velocity increases and so does friction loss. Compressor power increases accordingly. This is how hydrogen's low density translates directly into operating cost. Now consider ventilation. If a 500 kilogram per hour electrolyzer experiences a design leak of 0.1%, that is 0.5 kilograms per hour of hydrogen. Converted to standard volumetric flow, that is roughly 5.5 cubic meters per hour. To maintain hydrogen concentration below 1% by volume, well below the lower flammability limit, ventilation must dilute that leak by at least a factor of 100. That implies airflow of approximately 555 cubic meters per hour. In a 500 cubic meter room, that corresponds to just over 1 air change per hour. But industry codes typically require 6 to 12 air changes per hour, providing a safety margin above theoretical minimums. This is engineering conservatism aligned with physical reality. Step back now. Hydrogen differs from methane by multiples, not percentages. 4 times the diffusivity, 7 times the thermal conductivity, 8 times the flame speed, 14 times lighter than air. These are regime-level differences, and regime differences require architecture-level design changes. Hydrogen systems that survive under stress are those designed around hydrogen physics from day one. If ventilation is undersized, hydrogen accumulates rapidly at ceiling level. If pipe material is misspecified, embrittlement accelerates crack growth. If pressure drop calculations reuse methane assumptions, compressor loads are misestimated. If Joule-Thomson heating is ignored, thermal modeling is incomplete. Hydrogen exposes weak assumptions quickly. So the key insight of this lesson is not that hydrogen is dangerous. It is that hydrogen is different. Its physical properties redefine fluid mechanics, heat transfer, mass transfer, materials engineering, and safety engineering simultaneously. Designing hydrogen systems with methane intuition introduces hidden failure points. Designing hydrogen systems with hydrogen physics creates resilient infrastructure. As we move deeper into hydrogen engineering, into compressor sizing, heat exchanger design, storage modeling, and system integration, remember this foundation. Hydrogen is not lighter methane. It is a distinct thermodynamic and fluid dynamic regime. And every serious hydrogen engineer must begin here,